Hello, Science Alliance. Sorry, I was saying I've just done a Lego story show about the circus, which I think I might still have red paint on my nose, or I've just rubbed it. But anyway, I'm fine. I'm fine in myself. Hiya! It's the very start of our radioactivity module, so we've got. I haven't quite planned them all out yet, probably 7 lessons, because that's the amount of lessons there are until the end of term. On radioactivity, it's a fairly gentle start. We're going to start with atoms. A lot of this some of you will know already, but I've slipped in a little story which hopefully not a lot of you will know, which is interesting. First thing I've got to say is, I'm so sorry, there is a mistake on your printouts. If you've been to my website and you've got the printouts, then you will see a little picture like this, LI, and in the right-hand corner is a number 3, and in the left-hand corner is a number 3, in the right-hand corner is a number 4. Can you change that 4 into a 7? That 4 is supposed to be a 7, and it's not. Anywhere you see that, make it a 7 instead of a 4, okay? So, apologies. What a terrible first start. So, yeah, like I say, we're just going to start by talking about. Some of you are going to know this, but we're just going to cover everything that's on the specification, right? So if you already know it, that's quite good, because it means you're a step ahead when it comes to IGCSE physics. We talked about this in the periodic table lessons. If you got some aluminium foil and you split it in half again, and then again, and then again, and again, and again, and again, until you could not split that aluminium foil in half anymore, what would you be left with? Please have a think about that for 10 seconds. And what about water? What's the smallest amount of water you can get? What does that look like? And biscuit dough. What's the smallest amount of biscuit dough you can get? Let's do it. PowerPoint effects, yeah. If you split some aluminium foil in half again once, and then again, and again, and then till you had the tiniest speck of aluminium it was possible to have, you would end up with an aluminium atom. Yes, you would. If you split water in half again and again and again, you would end up with 2 hydrogen atoms attached to 1 oxygen atom. That is 1 water molecule. H2O. If you separated it anymore, you just have 2 hydrogens and 1 loose oxygen, and that wouldn't be water. That would just be those particles. They've got to be attached for that to be a water particle. And dough, it's very complicated. Dough is a mixture of different atoms that are bonded together. But what we're talking about today is atoms. So we'll focus on this. What actually is an atom? Well, I like to put an activity into all of these lessons. So if you've got some bicarbonate of soda and some vinegar with you, or even if you've just got some water and some salt with you, let's just marvel at the beauty of the world. There is so much in this world that we take for granted, isn't there? We know about atoms. You know that you're made of atoms. But you probably don't actually really think about it a lot. Or just, anyway. I was going to not even explain this, and then I couldn't help myself. I have got a bit of the chemistry on the screen. If you get bicarbonate of soda and you put vinegar in it, that happens. I mean, what a brilliant planet we live on. What is going on there? It's a chemical reaction, right? Atoms are popping off and rearranging. And even if you haven't got that stuff, you can just put some salt into some water, and what happens? It just disappears. Why? Why does it disappear? So people have been pondering these things. Humans have been on the planet for a while now, and we've been thinking about these things for thousands and thousands and thousands of years. Like I say, I wasn't going to tell you the science, but it is just super cool, right? Here's sodium bicarbonate, or bicarbonate of soda, as we call it in the UK. This is a particle, 3 oxygens, 1 carbon, 1 hydrogen, and 1 sodium, all bonded together. Vinegar brings the hydrogen particles, here they are, and one of them flips over and joins the sodium bicarbonate. You can tell I'm not a chemistry teacher, can't you? The sodium pops off, we're not bothered about what that does. What you end up with is this particle of what we call carbonic acid, but it's very unstable and it breaks down. Can you see what this particle of carbonic acid could possibly break down into? Well, a hydrogen and another hydrogen and oxygen go off on their own, and look at that. We've got 1 carbon and 2 oxygens, which is carbon dioxide. That's the gas. That's what makes the fizziness. It's that carbon dioxide being made and then escaping. And H2O, which, as we've already discussed, is water. So the Greeks Greeks did a lot of thinking, and the Greeks had definitely thought about the fact that there must be a smallest amount of substance. The Greeks knew stuff can't just appear and stuff can't just disappear. So they came up with this word atomos to mean uncuttable, like the smallest amount of substance that you can get, that you can't cut it anymore. And that is basically what atoms are. I have written it here. The smallest amount of a substance that there can be. The Greeks suspected this. Atomos in Greek means uncuttable. So there's two different kind of organisations that could write your IGCSE physics exam. There's Cambridge or there's EdExcel. We're just covering it all because, you know, you're home educators. You like to know stuff. It's fun, isn't it? And they're really similar. Cambridge want you to know a bit about the history of how the atom was discovered. And as far as I can tell, EdExcel don't. So if you're doing the EdExcel exam, you're not going to get tested on this, but it's just interesting. So here's the little story of how we discovered something about the atom. In 1897, English physicist J.J. Thomson, here he is, looking dapper with his moustache, discovered that atoms contained tiny negatively charged particles called corpuscles. Here's a picture of one. I've just done it as like a little tiny dot with a negative symbol in the middle. Tiny negative charged particle called a corpuscle. And then his friend suggested the name electrons, and he changed their name to that. So here's J.J. Thomson saying, forget that first thing that I said. It's an electron. Call it an electron. Here's very basically how he did it. You don't need to know this for any IGCSE physics exam. Basically, he applied a voltage to some atoms and realised that the things that sort of pinged off were attracted to metal plates. So he had this thing here, which old people watching like me, right, remember it, being in the back of TVs. It's called a cathode ray tube. And basically you get a voltage here and beams of electrons, which is the cathode ray, comes off this stuff. And these electrons are attracted. They move towards the positively charged plate in the cathode ray tube. So yeah, you don't need to know this, but this is what Thomson set up, and so discovered that atoms have got some sort of positivity and some sort of negativity in them. And this was very exciting. People didn't know this. We've known about atoms for thousands of years, but we didn't know that they had positive and negative bits. So J.J. Thomson explained this by saying, I think atoms are a little bit like Christmas puddings. The dough is like the positive bit, and then there's little kind of negative bits that I've called electrons dotted around in the positive dough, which is kind of like the fruit in a Christmas pudding. And this is famously known as the plum pudding model of the atom. Spoiler, it's not a very good model, which is why you've possibly never heard of it. The model got better. Because of this chap, Ernest Rutherford. So in the early 1900s, Ernest Rutherford, also sporting a magnificent moustache here, decided to test the plum pudding model. And this is the setup he used, and this is the one that you will, I think it comes up at A-level, but certainly if you're doing Cambridge IGCSE exams, they might ask you about this. This is the setup that Ernest Rutherford used. So it's basically a circle. We're looking down on it. You've got an incredibly thin piece of gold foil, like basically 1 atom thick piece of gold foil. And being fired at this piece of gold foil is radiation called alpha particles. We'll talk about what they are in later lessons, but they're basically quite big particles that have a positive charge, and they're moving really fast, and they're given off by this radiation source here. So you've got a screen, that's this whole circular thing here is the screen, which detects where these particles getting fired from the radiation source, detects where they go. And you've got a microscope so that you can see what's happening. And the microscope also can move in a circle all around the screen, all right? So the alpha particles, like I say, being fired out of the radiation source, they were, as far as atoms go, they're big. And they are positively charged, and they were travelling very, very, very fast. Here's what it looked like. Pew, pew, pew. It's not what it looked like. I just love my PowerPoints, don't I? Pew, pew, pew. And the gold foil was pretty much 1 atom thick. That's why they used gold, actually, because you can hammer gold down to be really thin and it won't crack or anything. And here's a little PowerPoint of the alpha particles travelling through the gold. So if the plum pudding model was correct, the thinking was that these big positively charged alpha particles that were going really fast would smash through the gold atoms and be detected on the screen on the other side. And that is very much mostly what happened. So on average, if you fired 8,000 alpha particles from this radiation source, 7,999 of them did pretty much go straight through the gold foil and were detected by the screen on the other side. But about 1 in 8,000 times. Oh, the big reveal. They bounced off. Great quote from Ernest Rutherford a while after this happened, when he was collecting his Nobel Prize. It was not expected. Rutherford said, "It was quite the most incredible event that has ever happened to me in my life." And then what I got told at university is that he said, "It was almost as incredible as if you fired a cannonball at a piece of tissue paper and it came back to you." Now, will you forgive me? Because this is theatre of science, right? We've got time. We're not in the classroom. Can I just do a nerdy side note here? This is what I got taught that he said. And it's an easy thing to imagine, isn't it? You can easily imagine how surprised that a person would be if they fired a cannonball at a piece of tissue paper and it came back. But it's not actually what he said when I looked at this quote for this lesson. He actually said, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." And I thought, oh, I wonder what a 15-inch shell is. So I looked it up. And it turns out, in the First and the Second World Wars, the BL 15-inch Mark I was a very famous gun used by the Royal Navy. Look at the size of this thing. So a 15-inch shell was the bullet fired by this gun. It was much bigger than a cannonball. It weighed more than a cow weighs on average. I really went down an internet rabbit hole on this one. So I thought, oh, that's really interesting. Rutherford was speaking about this in 1936, which is only like less than 20 years after World War I, and he had worked as an inventor for the Navy. I just thought, oh, it tells you a lot about what life was like at that time, that is where his head went to. It was like firing a really massive World War I Navy bullet at a piece of tissue paper. Needless to say, it was surprising. It was very surprising. Okay, so it meant that Rutherford needed a new model of the atom. Obviously, the atom is not what we think it is. If the atom can't be like this piece of tissue paper, if cannonballs or shells are getting bounced off it. So Rutherford realised that if most of the alpha particles did travel straight through, which they did, most of the gold atom must be empty space. But because, I'm just going to pull you back because I haven't seen you for a while. Higher. But some of them, very, very, very occasionally, these big positively charged alpha particles, if they were bouncing back, they must be experiencing a really strong force, just very occasionally, which is what made him realise that there must be a really, really dense area of positive charge right in the middle of the atom. And that's where we get this model from that you're probably more familiar with, this very, very dense positive kind of ball in the middle and negative balls on the outside. And he called the dense centre the nucleus, which is what it is called. You need to know that. And yes, like I say, he won the Nobel Prize for Chemistry in 1908. Well done, Ernest Rutherford. There's one incredibly important thing I've missed off about this setup that they might well ask you about. Can you get into the heads of Ernest Rutherford and his assistants, okay? You've just set this up. You've got your radiation source firing alpha particles, which are about this. It's basically a nucleus. You can imagine an alpha particle that is a nucleus being fired. You've got this gold foil, which is just one atom thick. You've set it up. Why can't you trust the results that you get? What have you forgotten? One really big important thing. We take it for granted. We don't really think about it, but in this situation, it's very important. You wouldn't be able to do that experiment without this one major step, which I haven't mentioned. If you want to go over to my Facebook page and prove to me that you've thought about it before I give you the answer, then feel free. There's air particles, aren't there? There's air particles over the place. You can't fire something that's about the size of a nucleus of an atom at atoms if there's loads of nitrogen and oxygen atoms all over the place. You've got to get rid of those air particles. So they did. This whole experiment was done in a vacuum so that they knew that it was the gold that the alpha particles were bouncing off, and they knew that it wasn't anything to do with the air. Well done if you spotted that. Okay, so this is more like the model of the atom that we have now. We now know that the nucleus of the atom, this bit in the middle, there we go, circled for you, contains positively charged particles, which are called protons. These things that I've done here in blue with a little p, that means they've got positive charge, they're protons. And neutral particles, that means they don't have any charge at all, called neutrons. Protons and neutrons are about the same size. Electrons are the little negatively charged things that whiz around the outside. They are tiny. By the way, I need you to remember this, okay? Protons and neutrons, positive and neutral, in the centre, about the same size. Electrons going around the outside, orbiting. So actually, we sort of show it as like a solar system situation. They're more like in a cloud, but it doesn't matter. They've hardly got any mass at all. They're a 2,000th the size of the proton or the neutron. They are so wee. So the nucleus is absolutely tiny as well compared to the size of the electron's orbit. If this atom was a football pitch, then that nucleus would be about the size of a golf ball. Another way of putting it, York, which is where I am, is very famous for having a minster, so I like this. I could picture it. Apparently, if the whole atom with a cloud of electrons around it is the size of a cathedral, then the nucleus would be about the size of a pin. Which actually, like, if you imagine sort of firing footballs through York Minster, you might hit a pin like 1 in every 8,000 times. Don't fire footballs in cathedrals, but it's a nice way for me to remember it. So the nucleus contains almost all of the mass of the atom, even though if the whole atom is a cathedral, the nucleus is just the size of a pin. So it's really weird because it's tiny, but also most of the matter is there. Right, that was absolutely loads of talking from me. Can you look at this diagram of an atom, please, and write down at least 2 ways it could be changed to make it more accurate? So it's just exactly the same little picture of an atom I showed you earlier. It's 2 protons and 2 neutrons in the middle, with 2 electrons whizzing around the outside. I think you should be able to tell me at least 2 ways now that this is not a good diagram of an atom. How would I can't make it perfect, but what 2 things are really, at least 2 things that could be slightly improved? Maybe I'll do it behind you. So the 2 things that I was thinking were, the electrons are a 2,000th the size of the protons and the neutrons, and here they're about half the size, so you could make the electrons smaller. That would be much better, to make them so small that they were barely there. The other thing is they're far too close, aren't they? If this is supposed to be a cathedral and the nucleus inside is supposed to be like the head of a pin, you want the electrons being as far away as you possibly can. So I've done this would be better. But obviously you've got to be able to draw it, so there's a limit, isn't there? But bear in mind this is a drawing. It's not that close to what an atom actually looks like. Okay, we say that protons and neutrons have a relative mass of 1. Relative mass means just compared to each other. And electrons have a relative mass of 1/2000th. All right, I hope this doesn't really confuse you. So here's a nice little table that I found on Wikimedia Commons that I think explains it well. These are subatomic particles, meaning sort of smaller than an atom, obviously, because they're what makes the atom. A proton is found in the nucleus, and we say it doesn't. This hasn't got a unit. It's not like 1 gram or 1 kilogram. It's just compared to the other particles. So a proton has a relative mass of 1, and a neutron has a relative mass of 1 as well. If you do physics for A-level, you'll learn what their actual mass is. But for now, we'll just say that they're 1 and 1. And the electron, you could say that its mass is 1/2000th of those other ones. Or you could just say it's 0, to be honest. Just say, if you ever have to do any calculations, like I'll make you do in a minute, just say that the electron doesn't have any mass at all. And it's the same with the charges. Protons have a relative charge of +1, and electrons have got the same amount of charge, but it's negative. So we say, again, at A-level, you'll learn these exact measurements, but we say that a proton has got a charge of +1, and an electron has got a charge of -1, just to show that they're the same but opposites. And the neutron has obviously got no charge, so that is 0. Okay, have you understood that? Can you tell me, please? Let's just work with our little helium atom that we've got here, 2 protons and 2 neutrons with 2 electrons whizzing around the outside. What is the relative charge of that helium atom, please? And what is the relative mass? And I've left the little table up there to help you. And apologies if you can hear my loft conversion going on in the background. I can't complain. This is deeply, deeply, deeply exciting, but also very noisy. Have you got that? So the relative charge, well, just add them all up, right? So you do 1 plus 1, because the protons have a charge of 1, and you can throw in a couple of zeros if you like to show that you've counted the neutrons as well. And then plus minus 1 plus minus 1, which confusingly makes 0. But this is right, isn't it? Most of you probably know that atoms usually have an overall charge of 0 because they've usually got the same amount of electrons as protons. So it usually cancels each other out. They don't have to have the same amount of protons and electrons. It's the number of protons which says what an atom is. So if this helium atom lost an electron, it would still be helium because it's got 2 protons. If you add another proton, then you haven't got helium anymore. But if it's got 2 protons, whatever else is happening, if it's got 2 protons, then it's helium. It's the number of protons that decides what the atom is, okay? Right, the next one, the relative mass of this helium atom. Did you get that it was 4? The electrons don't count, they're just negligible. You can say 0. I think probably in an exam if you said 4 and 2,000, it wouldn't be wrong, but let's just say 4. 1, 2, 3, 4, because the protons and the neutrons weigh 1 each. Right, here's a periodic table. The atoms are listed in the periodic table in order of how many protons they have. You know that if you've seen my periodic table lessons. So here's hydrogen with 1 proton, helium with 2 protons, lithium with 3 protons, beryllium, you get it. The number of protons that they have. The posh word for that, which you need to know, is it's an atomic number. So lithium has 3 protons in its nucleus. So we say that its atomic number is 3. And because scientists love to confuse you, you could also call that the proton number. That wouldn't be wrong. Your exams would accept that as well. So the number of protons in the nucleus of an atom is its atomic number or its proton number. For me, that's not that hard to remember because it's the protons that make the atom what it is. So it's the atomic number because, yeah, it's the number of protons that make it that atom. Okay, go on then. How many protons does calcium have? Looking at this little chunk of the periodic table. I haven't done any tricks. You don't need to remember the symbols. It should be fairly obvious. How many protons does calcium have? How many protons does calcium have? That's the quiz show song for this quiz. It's 20. Calcium has 20 protons. Did you see it? It's just there. Let's do that again. How many protons does lithium have and what is its atomic number? How many protons does lithium have and what's its atomic number? I'm trying to make it seem harder than it is because it's just 3, isn't it? The atomic number is how many protons something has, so it's 3. Yeah. Go on then, what's the proton number of nickel? What's the proton number of nickel? It's... Can you see it? 28. Yeah, I was just trying to get used to the words because there are more words coming and it gets a bit confusing. Yeah, the proton number, the atomic number, how many protons nickel has is 28. Yes. But if you've ever looked at a periodic table, you'll see that there are 2 numbers next to the element. What does this number on the right mean? I'm not going to tell you. I'm going to just flick through and see if you can work it out. So we've learned that the number on the left is number 2, if this is a helium atom. The number 2 is the atomic number, the proton number, the amount of protons that it has. And here is a picture of the atom showing 2. What does this number 4 mean, though? Here's another example, see if you can work it out. So lithium's got an atomic number of 3, that means 3 protons, there they are. But the number on the right-hand side is 7. So what does that mean? What does the 7 mean? Lithium's got 3 protons, 4 neutrons, by the way, and 3 electrons. Here's another example, carbon. Are you formulating some kind of theory? Carbon's got 6 protons, it says here, that's its atomic number. And the other number is 12. What does that mean? It's got 6 protons and 6 electrons and 6 neutrons. And finally, can you work it out? Oxygen, its atomic number is 8, and this other number is 16. And oxygen's got 8 protons and 8 neutrons in its nucleus and 8 electrons whizzing around the outside. The answer is, it's the number of protons and neutrons added together. And this is the other thing you need to know. This is the atom's mass number, or you could call it the nucleon number, because nucleons are protons or neutrons, because they're found in the nucleus, so they are the nucleons. It's a lot of words, isn't it? Protons and neutrons are both nucleons because they're found in the nucleus, and the number of protons and neutrons added together is called the nucleon number. Makes sense, doesn't it? It's the number of nucleons. Or the mass number, because that is where most of the atom's mass is. I feel like I just said loads of words in a row then, but hopefully you've understood that. So you quite often see this sort of thing in exams. They'll show you this lithium with a little number 3 and a little number 7, and they might say, how many neutrons does lithium have? And you'd have to think, oh, okay, I know that it's got 3 protons because that's its atomic number. I know that it's got 7 protons and neutrons added together because there's its mass number. So if you take away 3 from 7, then you're left with 4 neutrons. So lithium must have 4 neutrons. That'd be a nice question at IGCSE, wouldn't it? Right, but excuse me, we'll just cover this quickly. You will have noticed, if you've ever looked at a periodic table, sometimes this mass number looks really weird. Like, here we go, iron's got a mass number of 55.85. What's that about? How can you get 0.85 of a proton or a neutron? It doesn't make any sense. Well, this is what we'll talk about next week. It's the number of protons that decides what an atom is. So this atom, for example, lithium here, can have different numbers of electrons and it's still lithium because it's got 3 protons. But it can also have a different number of neutrons and still be lithium as well. And sometimes atoms do have different number of neutrons. So atoms that have the same number of protons but a different number of neutrons are called isotopes. So here we've got 3 pictures of hydrogen. It's hydrogen in each case because it's just 1 proton, which is what makes it hydrogen. But in the first picture, it's just got 1 electron going around it. That is the most common hydrogen atom. But if you add a neutron, it's still hydrogen. It's what we call heavy hydrogen, but it's still hydrogen. And even if you added another neutron, it would still be hydrogen, but these are all different isotopes of hydrogen. All right? Okay? Awesome. So if the protons and neutrons added up looks weird, it's because this number is the average number of neutrons. So some lithium atoms have 3 neutrons, some have 2 neutrons. So they've taken an average here. You can look that up in your own time. You don't need to know about that number. But it is the differing amount of neutrons that makes an atom radioactive. So we will do more about that next week. Okay. Woo. Are you ready for your questions? So if you've printed off your printouts from my website, they're optional. It all goes on the board, but you can have a look at that page now. You've got 8 questions in front of you. We'll go through these questions and then, and then we'll go through the answers. And then we'll see if you learned something. Hopefully you did. Here we go. Question number 1. What historical model of an atom is shown in this picture? So you've got a beautiful, big, red ball of positivity with some little negative balls dotted in it. What's the name of that model of the atom? Excuse me. You got it? If you know it, don't you? The point of these questions is to make you do a little bit of trying to remember stuff. Who proved this model was wrong? Which scientist proved this model was wrong? So that model of a big lump of positivity with little negative bits in it is called a certain thing. Who proved that model was wrong? I'll be kind and give you some choices. Was it A, Ernest Rutherford, B, J.J. Thomson, or C, Marie Curie? Next question. Question number 3. Which particles are found in the nucleus of an atom? It's really mean to not give you a picture here. Which particles are found in the nucleus of an atom? Is it A, protons and electrons, B, protons, neutrons and electrons, or C, protons and neutrons? Which particles are found in the nucleus of an atom? Protons and electrons, protons, neutrons and electrons, or protons and neutrons? And then the same choices again, but a different question. Which particles have a charge? Is it protons and electrons, protons, neutrons and electrons, or protons and neutrons? Which particles have a charge? Question 5 out of 8. What do these numbers on the periodic table mean? That's a bit of a mean question, this actually. Question 5, what do they mean? I just want you to write it in your own words, please, as if you were explaining to someone. So not like the name of the number, just what does it mean in your own words, if you could. What do these numbers on the periodic table actually mean? So you've got a picture of lithium here, and on the left-hand side is the number 3, and on the right-hand side is number 7. What do those numbers mean? What do they tell you about lithium? And then if you've done that, I also want you to tell me the proper names for them. So what do those numbers mean and what are they called? There's two different choices, aren't there, for each one? Is that okay? Should we move on? Are you racking your brains? Number 7. 2 atoms with the same number of protons but a different number of neutrons are called 2 atoms with the same number of protons but a different number of neutrons. What are they? Are they isobars, isotopes, or isotopes? Isobars, isotopes, or isotopes? So if I'm doing a lot of tapping and clicking, it's because my loft conversion people upstairs are playing some really banging tunes, which I'm hoping that you can't hear, but you're getting them secondhand from me. And finally, it's quite a lot of work for the last question, sorry. Can you label this diagram of an atom? So you've got 4 labels here. You've got an atom, some positive balls right in the middle. What are they called? Some balls that don't have any charge. What are they called? Some little negatively charged balls whizzing around the outside. What are they called? And also just the overall clump of positive and not positive balls in the middle. What's that whole clump of stuff called? I suppose actually you could have 2 words for C, couldn't you? Yeah, you could. If you're feeling like this is too easy for you, you can write down both words for C. Okay, let's go through the answers. Excuse me. The answer to question number 1. This is the plum pudding model. What a lovely name for a model of an atom. The plum pudding model, which was sort of thought of by J.J. Thomson, and then proved wrong. The plum pudding model was proved wrong by Ernest Rutherford, who came along later and discovered that actually most of the atom, the vast majority of the atom, is empty space. Someone on the Facebook comments yesterday was saying, so does that mean that most of our bodies are empty space? And I was like, yeah, it's weird, isn't it? Because you want to think about, like, when you think about empty space, you still imagine there being air, don't you? It's easy to imagine that in this atom there are air particles, but obviously there aren't because air is made of atoms. So there's no atoms fitting into the air. It's just very weird. It's going to get weirder and more wondrous as we go along. Which particles are found in the nucleus of an atom? That was protons and neutrons. These are the 2 particles that are about the same size. Protons and neutrons, also called nucleons because they are in the nucleus of the atom. At A level, you'll learn that the neutron is just a teeny, tiny bit heavier, if memory serves. And which particles have a charge? That one is just the protons and electrons. Neutrons do not have any charge. They are neutral. So it's just the protons and electrons that have a charge. Question number 5. What do these numbers on the periodic table mean? The little number 3 is the number of protons, and the little number 7 is the number of protons and neutrons added together. If you said the number of nucleons, then that's fine. Although probably in an exam I would write number of protons and number of neutrons added together just so that they knew that you knew. And what are the names of those things? Oh, I'm going to show you the symbols now, and I'm so sorry. I just apologise on behalf of science for the symbols that they use. The number of protons is the proton number or the atomic number, and the symbol for that is a Z. We'll talk more about this later. Proton number or atomic number, well done if you got either of those. Symbol Z. The nucleon number or the mass number is what you would call the 7, and the symbol for that is an A. I don't know why the symbol for atomic number is not A, the atomic number is Z, and the nucleon number is A. I'm just really sorry. We'll just have to say it a lot over the next 7 weeks so that you get used to it. But yeah, proton number or atomic number would be fine in your exam, and nucleon number or mass number would also be fine. Number 7, 2 atoms with the same number of protons but a different number of neutrons are called isotopes. They are isotopes. And finally, this labelled atom. The A, the tiny little negatively charged particle, is an electron. The neutral particle in the middle is a neutron. And I've put that C, D is the proton, so the protons and neutrons are in the middle, and I've said that C is the nucleus. But if you'd also written nucleons, that would not be wrong. That would be good. I would be impressed. But I reckon you should write both if you do. That happens to you in an exam. And there you go. That is the end. People on Facebook yesterday were telling me what they got out of 8, and I was really trying to politely say, I don't really care what you got out of 8, because it doesn't really tell me anything. That's the thing. Whatever you got out of 8, like if you got 8 out of 8, that might mean that you knew all that already, and I haven't taught you anything, which for me would actually be quite sad, because I'd kind of wasted your time. If you got 2 out of 8, it might be that you didn't know any of that before, and you were really exercising your brain muscles to remember 2 of the answers, which would actually be great, like from a teaching point of view, because you've learned something. So yeah, well done, whatever you got out of 8. And the whole point really of me asking you questions like that is to try and get your neurons fusing by making you remember things. So if you got out of 8 out of 8, maybe it was too easy. Maybe next week I have to try and make it harder. Oh no, here's Eleanor, brilliant. Just come onto my, and Anthony's here, pics posted. Yeah, no way, oh that's awesome. Okay, Anthony is an ex-circus performer, so watched Lego Storytime about the circus. So I will be going to look at those later. Thanks, Anthony, that's so cool. Oh, Eleanor, thank you for watching and for letting me know that you are watching. That is very nice. And the rest of you lurking, hello to you as well. Hello, I never say hello to your lurkers. I don't want to embarrass you, you know. Maybe you like lurking. I don't want to call you out, but anyway, thanks for being here. It does make a big difference seeing numbers on the screen. Right, so that's the end of that. Like I say, I don't actually know how long we're going to be doing radioactivity for. I'm hoping it'll fit beautifully into the next 6 lessons, because then we've got a holiday coming up. And then it's astronomy, and then we will have done an entire IGCSE physics course together, which is really weird and amazing. But yes, I'll be back next week. Look out for the advert, but you know, it'll always be really easy household stuff that you need to bring. Yeah, my lesson on fats, if you come to my all ages lesson, it's on nutrients this term, and we're learning about fats tomorrow on YouTube at 9 o'clock, if you want to come to that. If you want to support me, you totally should. That would be much appreciated. If you go to my About section on YouTube, go to my About, like and subscribe first, and then go to my About section, and it takes this website called Coffee, and you can support me with £5 a month, and it's just desperately appreciated. People who support me receive Theatre of Science magazine whenever I've finished it, and the latest one is the latest it's ever been. It's so late, but I have now finished it. If you are supporting me, I'm so grateful to you for your patience. It's so lovely. Yeah, it's done. It's going to be coming back from the printers and put into boxes and little free things added and then posted out to you, but I'll tell you when to get excited, because it's just a really long process. But at least it's finished. It's out of my head now, which has pleased me greatly. But if you sign up to support me now, that's what I was going to say, then I will send you a little welcome pack with a past issue of Theatre of Science magazine in it to tide you over until you get the new one. So if you sign up now, like if you're watching live, I'll send you this issue which is on weeds, which is good timing because all the dandelions are just coming out as I speak live, and it's got a little quiz in it about how to identify things that look like dandelions. It's got a comic, it's just got loads of cool stuff. I'm very proud of Theatre of Science magazine. It should be. It takes forever, doesn't it? And I'll send you some diffraction glasses as well, which will not be useful if you are doing IGCSE physics, because I'll also send you a little description of how they work. So sign up on Govy, £5 a month, get you those things, and my enduring gratitude, because this is clearly the best job ever. I am going to go and get that magazine off to the printers, just check through, make sure there's no mistakes, and I will see you all next week, if not before. Thanks for coming. Bye.